unlimited power. Well, something like that. It's just Blender. It's just proximity based lightning in Blender, and I'm gonna show you how to do it. Later on I'm gonna make 2 more tutorials. One of them is going to be arcing lightning within a single object, so it's not proximity based as much. And also I want to do lightning along a path, so stay tuned, subscribe to see those other tutorials. Okay, so the first requirement is Blender 3.1. This will not work in earlier versions, or at least it's way harder in earlier versions, so definitely use 3.1. And what we're going to do is just spawn in a cylinder. Okay, I'm just going to rotate this cylinder and open it up by deleting these 2 n-gons, and then I'm going to apply the rotation with Ctrl A rotation, and I'm going to spawn in a cube as well. I will move the cube slightly on X, and once again I will hollow it out so that we can see the inside. And then that will be about it for the setup. Make sure in the object properties that you have scale set to 0 on both objects, because that is important. And then we're going to move into our geometry node setup. Now mine looks different from yours, but don't worry, all you need to do is go into geometry node editor, just pull that up anywhere. You can pull up panels just by going to a corner, pulling them up and setting them up over here, and then collapse them by getting this little arrow downwards. But basically make sure you're in this editor. So first off, let's talk about how we're actually going to do this. By the way, click the new button to add the geometry nodes. They're located in the modifier stack as well. You can see our geometry nodes. We can go ahead and name that something like proximity lightning. Okay, and let's talk about how we're actually going to do this. So basically we have our cylinder, I'll represent it like this, and our hollowed cube, and it's something like this. And the first thing we're going to do is spawn a bunch of points on them. So a bunch of points on each of these objects, just like that. There's a node for that. It's called distribute points on faces. It does exactly what it says. And the only problem is that distribute points on faces node only has a slider for density. But what we want is the same number of points on both of our objects, so that then we can draw these lines between them, which are ultimately going to become our lightning in the end. Okay? So in order to make sure they both have the same number of points, we need to remember we need to basically set up our own density. And density is just the number of points per area, right? So we want to be able to control the number of points, and to do that we need to know the area of our 2 objects. First of all, we need to bring in this object into our geometry node setup. To do that, inside our group input for the geometry nodes, over here I'll click the plus, set type to object, and I will call this emitter, because it will be the thing that emits the lightning towards our cylinder. And then I will, over here in the modifier step, I will actually bring it in. It's called cube right now. And now if I just plug this into an object info, I will also have access to the geometry, to the actual geometry of the cube. So if I duplicate this, well, basically this is going to be my cylinder geometry, and this node here will be my geometry for the cube. Alright, so to get the area of these meshes, we're going to use a node called face area. Okay, so basically this returns the area for every face separately. It's like a field. That's what the whole fields thing is about. But we want to collapse that field into a single value, which is the sum of all the areas. To do that, we use something called an attribute statistics. And if I plug into here the face area and then the geometry of my cube, what I'm going to get out of this sum socket is exactly that, the area of my cube. I will do the exact same thing for my cylinder, where I will also plug in a face area node into the attribute. Okay, and then as we talked about over here, we have to divide the area, or rather divide the number of points by the area. So I will get a math node, and I will set it to divide, and put the area that we get out of this sum into the second socket. We'll do this twice for both of our objects. Sum into the socket, and then we're going to have a single value controlling the upper, because we want them to have the same number of points. I hope that makes sense, and all we have to do, actually before I do that, I would like to group all of this up, just so it makes more sense to me. Grouping things is easy. Let me just make sure everything is connected to one socket. This makes grouping later on even easier. And then I will just select everything here and press Ctrl G. This will group them up, and I can exit the group with tab. You can now see it, and I will call this something like even points. Even points. So if I hop into even points over here, I can get a single value to control both of these top values here in the divide nodes. To do that, I'll just drag one of them into my group input, and that will link it up outside of the group. Okay, and then I will also connect this up with the first point, with the first divisor of the second math node. Actually, to make this look better, you can shift right click to add a point here. That's a separation, and then you can drag that out over here. It's basically the same value. And then what we're going to do is we're going to plug this value into a distribute points on surface. We need this right now. Distribute points on surfaces, again 2 of them, and this is going to be our new density, which is based off of a specified point count. And now I just need to plug these points out here. I will go ahead and delete this node, the value node. We don't really need it. Oh, not that one. This mid node. There we go. And basically, I now have these 2 point clouds. Let me just rename the second one to emitter, so that I know that it's the one coming from my cube. And if I hop out of here, I can then hopefully just plug these into a join geometry node. Plug the points and the emitter. Technically they're both points, so maybe you would want to name this something like I don't know, object points and emitter points, just so we don't forget what we're dealing with. And then if I plug them into the output, we should be able to see them as soon as I set the number over here. Except we don't, because I didn't actually plug in the mesh over here. So you need to also duplicate this group input node with Shift D, and then plug our geometry up here. And similarly, we want to plug in the object info node, because it gives us information about our cube. The object info node right into, one second, the geometry right into mesh. And now we should, oh, this needs to be set to relative, by the way. The object info node everywhere needs to be set to relative, because otherwise it's not determining the cube as if I moved it. Basically just set it to relative. Alright, so then afterwards, let me select my cylinder again. Where did I actually go? There we go. We can see that we can control the number of points on these 2 objects with this single slider. And more importantly, they now have the same number of points. Over here 1, 2, 3. Over here 1, 2, and 3. There we go. And you can see the value here is 3. Basically it's a float. You can make it an integer. I guess this would be more logical. So I'll set this up to be an integer instead, and then it moves, you know, like an actual integer. 5 points equals 5 points, and so on and so forth. So now that we have an even amount of points on both of our geometries, what we want to do is cast a bunch of rays. So basically, I will once again draw the circle and the cube. We want to take one of these points, well basically any one, and cast a ray from it towards our target geometry. Okay? And for example, if I cast a ray from here, this ray doesn't make much sense because it's sort of intersecting our cube. We don't want that. So we want to test these rays against the cube as well. And then we want to check, did we hit our cylinder? And if we did, keep the ray. If this didn't hit the cylinder, no ray. Okay? And that will make sure that all of our rays are only rays, or rather, all of our lightning will be only lightning that has direct field of vision towards our cylinder. So, let's get our raycast node. And I guess we need to talk a little bit about that. Target geometry is what the rays are tested against. So we want target geometry, as I talked about over here, to be both our geometry on the cylinder and also, if I plug out an object info, the object over here. So we want to join these 2 geometries, just like that, like this, and then this is going to be what we're going to be testing the rays against. Next up, we need to determine the, well, what is it? The source position. So this is where the rays are coming from. So the source position will be the points that are on our emitter. So we need to get their position, and to do that we will use transfer attribute. We will plug that right after the emitter points, and the attribute we want to transfer is position. Basically the transfer attribute node we want to set to vector and to index, and then plug position to attribute. What this node lets us do is take a certain attribute and use it directly from a certain location. so it doesn't have to guess things off of context, for example. I will temporarily remove these points. We don't need to see them right now. And we're going to want another attribute. Well, first let's plug this in, because this is indeed the source position of our points. And now we can talk about the ray direction. So if we know the position of these 2 points, let me clean this up a little bit. Basically, if we have 2 points and we know their position in world space relative, well, technically it's in object space, so this is my object origin right here. Well, their position is relative to the object origin, so we can think of it as a vector that goes like this. And funny thing, oh, this is not quite right. Funny thing about vectors, when you subtract them, you actually get another vector that is between the two. Okay? And the direction in which you subtract them also determines in which direction the ray is facing. Alright, so we can use this to get the direction of our rays. Basically, we're going to subtract the position of the emitter from the object points, and to get the position of the object points we need another transfer attribute, which is basically the same setup right here, but for the above. And then, like I said, a vector math node that will allow us to subtract one position from the other. And then this thing is going to be our ray direction, which will plug into that exact thing. Alright, so far so good. Next up, our rays, in order for us to actually see them, we need to set an object for them. So I'm going to use instance on points, and the points I'm going to instance something on are actually the points of my emitter. Actually, at this point, it would be pretty good to group things up. Again, because otherwise things get very messy. So I'll grab all of these top nodes and press Ctrl G to group them up. Okay, and now we can see that we're pumping into them the geometry, the emitter, also ray direction, that is exactly what that is, and the source position. We can rename that to ray source, and I would also swap these out so there's not as much spaghetti going on over here, something like that. And then if I just delete these doodles once again, we will see what I mean. Why we separated this into a separate group, because now I can just take this out and connect it a little bit better. It just looks way better. So next we want to actually see our rays. To do that, instance on points, and the points we're going to be instancing on are the points of our emitter geometry. So we also want to pass that into our node. That would be another geometry socket that will just be on, yeah, it will be a geometry. We can actually call it ray points, I guess, or rather just emitter, because that's what it is. That will get confused with the other emitter, so let's just go emitter points. Now if I hop out of this, I can plug the emitter points, which are this socket right here, into this emitter points, and then I can tell it to instance on them. The thing we're going to be instancing is actually a curved line, just because it is the simplest thing that has a start and an end. I will plug the curved line into instances, and then I will get these instances and plug them out. I will hop out of here and actually connect this to our geometry output so we can see them. And here they are, our instances on our 3 points. Well, I can bump up the number. There we go. On our points, and the first thing we're going to realize is that if these are supposed to be our rays, first of all they need to be facing our geometry. Okay, so to do that we already have the direction of the rays. All we need to do is align UR to vector, which will align our line with this vector of the rays. So plug that into rotation, plug ray direction into vector, and set this to Z. Now we can see our rays are facing, well, I should actually show our other geometry. So I'll hop out of here, I'll do a join geometry, and I will plug into this a copy of our original geometry. Now we see both of them, and we can see how the rays are going towards our geometry. Now first problem, they're kind of short, they're all the same length, but luckily the raycast node has a hit distance, and if we plug that into our scale, that will straight up scale everything. What's up exactly? Relative. Never forget the relative. Always, always, always. Yep. That definitely probably what messed me up. If I do increase the count here, yeah, this is what we want. This is now working correctly. So what you're gonna notice is a lot of these rays are intersecting this geometry, but they're still here, and we don't want to see the rays that don't hit our cylinder. To do that, I will hop back into this group, which I will probably rename curves, because ultimately this will give us the curves of our lightning. We want to use this custom attribute on the raycast node. So basically the custom attribute is something that is tested against. If I take my original geometry, I'm just moving things around a little bit, and then use a capture attribute. So this is my cylinder, and what I capture on it is a boolean, and I set that to yes. What that means is that every point, because that's what I've selected, on my cylinder will then have a value of 1 associated with it. Okay, and that will be in this attribute. So I'll plug, oops, that will be in this attribute, which we need to plug into here, into our raycast node. And instead of float, set this to boolean, plug this into here, and now the raycast is also testing for this attribute on the geometry that it is testing against. So basically my cylinder does not have, the cube doesn't have this attribute anywhere. So if a ray hits the cube, the value that is returned by this attribute will always be 0. But if it hits the cylinder, or rather the cylinder, the value it returns will always be 1, because I gave it a value of 1 right here. Alright, so now that means that what I can do is just take this attribute right here, oops, I accidentally undid that, and plug that into selection from instances. And boom, all of those are gone. Now we only have the rays that are directly facing our cylinder. Let me bump out their count ever so slightly so that we can see them. And now if I move this cylinder around, we can see how they're all basically working fine. Yep, I'll leave it to something like that. You know what, maybe I will subdivide this mesh, because it's way too sharp right now. The edges are creating some issues. I will just go into edit mode, select all faces with A, then right click subdivide. That won't help me too much, so I have to soften them up manually a little bit. So scale with Shift Y, so I'm only scaling on the Y. Oh, I selected one more than I needed to. So scale on Y. That's a bit better. Now it's more of a cylinder, but now the points are more evenly distributed because we have more geometry, and that's really what I wanted to get at. So if I go back into my geometry nodes, now the count seems way too high, so I'll lower that to like 100. And also for this point, you can add a seed value. So if I add another integer and I call that seed, I can then connect this up with the seed on my distributed points nodes, so that I have a little bit more control there. There we go. Just like that. And now if I hop out of here, I should be able to control the seed of my rays. And basically we're done with that. We're done with the selection. And at this point we need to talk about the radius. So raycast length will be what we use to determine the radius at which lightning is affected, because it determines the maximum length that rays can travel. And if I set that to 0, they will all disappear. But if I change that even a little bit, you see if I do it enough, they start to increase based on the distance. So this will be the radius of our effect. We can go ahead and plug that in. If I can just plug this in like this, and then just rename it to radius. That's the radius of our effect. Alright, so the first thing we want to do is then realize these instances, because we want to be working with the curves of our mesh. If I plug that back in, you can see we have our instances. They're just rays right now. The first thing is to resample them based on length. I'm just going to give it the default value of 0.1. And then we want to arc them. We want to give the lightning some character. So to do that, I'm just going to use a set position node, and I'm going to link that up with a noise texture. What I have to do, however, is run the noise texture through a vector math and subtract from the color attribute 0.5. This is because, you know, all of the color that comes out of the noise texture is RGB, which is 0 to 1. But that would imply that it will always be in the positive direction of the coordinate plane. So over here, but what we want is to shift it all with 0.5, so that it's minus 0.5, you know, 0 and 0.5. basically around the center of our coordinate plane, and because we just have the value, we also want to boost it up usually. So the issue is that if I now plug this right into the offset, we get a lot of noise, and this is what we want. However, we want this noise to be much finer, so set detail and roughness to 0 and the scale to something low, probably like 0.5 if not lower, and that's how we're going to get this arcing effect. Now the issue is it's currently working on the entirety of our spline, but we want the arcing effect to be most pronounced in the middle of the spline. So to do that, we have to modify our spline parameter a little bit, more specifically the factor value. So currently, if we have a spline, the factor value is 0 to 1, but what we want to get at is something that goes 0, 0 with 1 in the middle, so kind of like a U-shaped. And this is, if we plot this out in a coordinate plane, we'll see that as the length increases, you know, if y is here, x is here, this is just a linear transformation from 0 to 1. Right, if this is 1, then we will also have 1 on the y. But what we want to get is more curved, so basically if this is a coordinate plane, what we want to achieve is like this weird curve right here. Like it has 0 at the start and at the end, but if we continue that, we'll notice that that is just a parabola. So if I hop into Desmos and I say y equals x, that's the linear transformation that we have with the regular function. But if I square that, we'll see that that's a parabola. If I flip it with a minus beforehand, we'll get this, and then if I add an x, it will basically center it exactly where we want. Afterwards, if I just modify all of that with a multiplier, something like a, I'll be able to change the strength of this transformation as well. And to do that with nodes, simply take your spline parameter, pump that through a math node, and then that math node I will set up to be power. Plug the factor here, change the exponent to 2, multiply this node, multiply again, set it to -1, plug the output, and then what we have to do is add to this the original factor, and then run that through another multiply node. Okay, then since we're going to use this probably more than once, I will group it up, and I will just call it a UMAP. And what we want this UMAP to have is an output for the final value, but also a control for the multiple at the end, which I will probably just call scale, which will basically be the maximum value of this map we have created. Alright, now if I hop into here, I'll set the scale to something sensible, and maybe I'll change the default of it to 1, and now we have access to this. So if I then run this through another vector math node in between here, and I multiply the noise by this map, we will see that now the noise is only affecting the middle, and we can change the strength of it like this. Now another issue is that the noise is moving quite the same way, quite coherently. That is because each one of these curves is basically using the same spatial parameters for the noise, and what we want is to offshift that, or just shift that a little bit using a certain number. So basically we want a unique number for each one of our curves, and that is what we're going to plug into this W parameter, which is like the shift forward. Let me just give this some noise so you can see what's happening. So as I'm changing the W, you can see the noise is shifting, and I want a unique number plugged in here that is associated with each spline. The easiest way to get that is to get an accumulate field node. So the accumulate field node, if I set it to integer and set this from point to spline, means that it will take the value of 1. Basically, how to explain this? If you have multiple splines, this will return a value of 0 for the first one, 1 for the second, and so on and so forth by accumulating whatever value is passed into this socket. So if I set this to 2, then the second value would be 2, and the third one would then be 4. And that's how I can set up a specific number for every point along my spline. So all of these would be 0, and so on and so forth. So that will allow me to get a unique number that I can then drive every spline's noise with. And what the difference is between leaning and trailing is basically if I use trailing, I will get this configuration, but if I use leaning, the first one would be this number, so it would be 2, 4, 6. In this case, I'll use trailing because that just makes more sense to me, but you can use whatever, and I'll set this to a high value so there's a bigger difference between each spline, something like 5 ought to do. And now if I just set another math node, I can still make use of my W parameter by shifting it like this, and now you can see that they're moving mostly randomly. So we have now offset that that equalityness, or just equality that was before, and we can continue with, well, basically if our arcing is done, because now we can control the strength of the arcing and the noise, which I would honestly lower even more to something like 0.5. Now we can make our lightning arc quite a bit, and if you're further away you might want to bump this value up so that it arcs more in random directions. But basically we want to take all of this, including the set position node, and group it up, and we will call this arcing. And of course we want to be able to control a couple of things, so I would take the arcing's group input and I would just add to it like the scale here. And also I guess I want to shift the W, so I'll add this thing and I'll rename it the W, because this is now our control for the noises W. Another thing we want to control is the scale. I'll plug that in, and I guess now we have two scales, so I'll call the second one boost, because it is basically a boost to the arcing. And we're really done here. So this is going to be our arcing. We have full control over it, and basically in order to get noise, because that's what we want next, it's pretty much the same node, so I'm just going to duplicate this, but also press this number to make it a unique node. I'll plug this in the middle, and the noise we're going to be adding along this lightning, the only difference with the arcing is that it doesn't really need accumulate field, so you can trash that, and you can control the W directly. And in fact the scale just needs to be much finer, something like 10 for example, or no, I mean the scale. Actually the scale here is very big, which means it's probably not connected to the right thing. Yes, indeed the scale is not connected correctly here. Just give me a second to fix that. There we go. So now this scale is controlling, or is it? Scale to scale. Scale to scale, W to W, and boost to boost. Yeah. And the scale should be, except my boost is very low. That's probably, I'm gonna just mute the second node for now, because I kinda messed up my connections here. Basically we want this at 0 to 5, and we don't want the boost to be too high at this distance, and the W still works. Alright, so for the second node I'll unmute it now, and I'll actually mute the arcing node. I will rename the second node to noise, because that's what it's going to be handling, noise along the actual lightning. And what we need to change on the second node is again the basic setup that's here. The difference is that the scale is much finer. So I'm going to reconnect the scale. This one is also inappropriately connected. I'm sorry, I messed these up a little bit. So just make sure the names are correct. Okay. Yeah, so a very fine scale here. You see that as you increase the scale, it gets more noisier with a little bit more boost. There we go. There we go. That's pretty much what we want. Should go ahead, play around with this. What you're gonna notice though is that after I enable the arcing, the lightning might behave a bit weird. Like it's a bit stretched. There's a lot of it here, but not so much over here. That is because the arcing, if I disable the noise, stretches out these splines quite a bit, and that means uneven points along the spline. So to fix that, I will simply plug in another resample curve with the same length as the first one. Okay, and yeah, now you can see we have more even distribution of lightning, but except not at the end and start, because that's what we want thanks to our UMAP. I guess you would need to control this from the outside, the resample amount. So I'll plug that in, and now we're done with the arcing and the noise. If I then have a single value driving their W, we should get a fairly cool effect. Yep, there we go. We can see our lightning just sort of moving. And by the way, the whole thing should pretty much be working now. If I just, yeah, there we go. You can see we have our distance-based lightning. Now, lightning doesn't really just have these things going for it. It also has forking, like these electricities would like spike in different directions, and that's what we're gonna do next. I'm just gonna boost the lightning a little bit here. So the forking, to do the forking, first off we'll need a joint geometry node in the end, and the forks are basically gonna be copies of these splines. So I'll copy them using instance on points, and to have a specific number of copies, I'll just use the mesh line. If I set it to 2 and set everything else to 0, that will give me exactly 2 copies, because that's just the number of points I want. And what I want to be copying is of course this geometry, so that's my instance, and then I want to join these instances with the join geometry node. Then I'll go ahead and group these things. I will call this forking, and basically this should be the setup at this point. And now in here we need to actually have some controls. The count, the number of forks, is just the count on the mesh line. Of course we need to realize these instances. Set position. Okay, and then we're going to push these splines, because they're currently overlapping with the original splines, along the normals. So we've done this before. Just take normal, vector rotate, plug that in, and we're going to just rotate the normal vector around the tangent. So tangent, vector, normal, and the value we're rotating with is going to be random. So we once again need a random value for each spline, so we know how we do that now. Accumulate field. It's probably fine to just leave this at 1. All I need to set this is to integer, and then spline, and then I will use this random value, or rather this unique number, to drive a random value, and this random value will be between 0 and 2 pi, because that's a 360-degree rotation radians, and then I'll just take leading, or rather trailing, and plug that into the ID. So as soon as I connect this up to the end, I should see all my splines rotated around the original ones, but I want them to be rotating more as they get towards the end. So to do that, a vector math node set to multiply. In between here I will plug in a or rather just the spline parameter, because the spline parameter goes from 0 to 1 towards the end, and we want this effect to be stronger at the end. Of course, some way to control this would be nice, because it's too strong right now. So a math node right after the spline parameter, and now see, we can control that. However, I chose spline length. I need spline parameter. My bad. Spline parameters factor. Alright, there we go. So as we're getting towards the end, now we're pushing away in a random direction. However, this is very linear, so I would also pass this factor through another math node that is set to power. And what that will do is it will take this linear transformation and just taper it off, because that makes more sense to me, at least. So set that to 2, and now, in fact, maybe even 4. You will see that we're really forking out as we get further towards the end. And another thing is, currently we are splitting at the start. We don't really want that. We want to split these forks at random locations along the original lightning. To do that, I will use a map range onto which I will pass. Yes, this map range has to be before the control for the scale. And what it needs to use is this minimum value. You see, as I change the minimum value, we're splitting higher and higher along the chain. And basically, I'm going to plug a random number into here. So I'm going to copy this random value. And if I set it to 0.1 and 0.9, then somewhere along this factor of the line, it will split up. And then again, I will load up the ID, and I will set a minimum value. So if I change the seed, now our lightning is splitting from the original at a random location. Alright, so then after that, the problem is that all this residual lightning is the same length as the original one. I guess you can't really see that. If I hop out here to reduce the number real quickly, because we have way too much lightning. 1. Perfect. That'll probably be fine. Hop back into the forking node. You will see that we do have 2 splines going out, and I can change it with the seed. But the issue is that, well, first of all, they're all rotated the same direction. And why is that? Because this needs to be a bit higher than 1, otherwise it doesn't count correctly. Yeah, so accumulate field has to have a slightly higher value, I think. Yeah, now they're random. Now they're essentially random, but they're all the same length. So to change the length, I will give it a delete geometry node. The delete geometry is going to work based off of selection on the spline parameter. So what I'm going to say is that if the factor is above a certain value, so greater than, and this is the factor, if the factor is greater than a certain value, which will be a random value, and the minimum for this random value will be the value we get from here, well, the maximum could be somewhere along towards the end. 0.9 is probably fine. And if I now plug this in here and this in here, you will see that it's now cutting them off at a random distance from the end, and I can change that distance. Yep. So exactly what did I actually do here? Let me explain it a little bit more. We have our original lightning. We spawned a bunch of lightning around it, and then we rotated that lightning randomly using the accumulate node set to a pretty high value here, and 0 to 1, this whole thing. And then I just chopped them off at a random location that is between this point and the end factor. So for these splines it would be this point, and the way I did that is I grabbed the result I got from here, which is the way we split them, into the result I get here, which is the way we delete them. Okay, so that was a random value between this interval, and that's for each one of them. I hope that makes sense. Let me just delete that. And now you can see we get a pretty good result. I can move this object around and we can see it's zapping. It's zapping, alright, and we have these forks. Now we can also change how far the forks spread out from the maximum value over here. We can change how far these forks go or where they start to spread out from. Currently it's just random between 0 and 1. Basically you want a control for this, so I would grab my group output and I would take this to maximum and plug it here. And I guess you can plug in a control for these random values as well, where they start to fork from and etc, but I won't do that right now. I really only need a control for the total count and how much they spread out. Okay, and other than that, I suppose all we need to do now is get out of here. So this gives us our curves. All we want to do is turn these curves into geometry. Although I guess you could do that inside the curve as well, but should I? This got too long, that's why I don't want to continue working inside this node. So to make these curves into geometry, by the way, these are not instances, I need to rename this to curves, because that's what comes out of here. We want to use a curve to mesh, and curve to mesh, and what we're going to pass into the curve to mesh is a circle, a curved circle. I'm going to pass this right into here. And also what needs to be controlling this this radius here is a set radius, because set curve radius, the radius is how it determines the depth here. And I need the radius to be based off of the spline parameters. So spawning a spline parameter, which already goes 0 to 1 from the start to the end, plug that into here. And then I guess I would need to also flip it, because it seems to be going in the wrong direction. So to do that, just a map node, just set to subtract 1 from that flips it, and then we can control the total radius from over here, rather the maximum radius. I'll disable my overlays from over here, and you can see now we have some geometry for our lightning, and we can also control the thickness for it. However, I would group all of these nodes that are related to the geometry, and I would call this something like solidify. And I would also give some noise to this. Currently it's way too linear, so just a little noise texture. This just gives a little bit of randomness. I will not touch it any more than that. So that would be the scaling. And now that we have our geometry, which we want to give some control to, for example, we want to control the radius, which is basically the maximum radius, and the resolution would be fine if we have a control for that as well, because honestly it doesn't need to be above 6. This geometry is so thin that it wouldn't be an issue. Alright, so then we're almost there. Really all we need to do is just give it a material. So I'll set material, and I will need to plug this material into my group input for the geometry node. So set this to material, and then I would have access to it from over here. And then I would go into my object and I would add one material, set it as default, and then another material which I will call lightning. So in the shading editor, or rather in the geometry nodes first, let's set this up to lightning, which is better in my if we connect it through our modifier, so lightning, and then I have it over here. It's called emitter, it ought to not be. Material. And if I go into rendered mode, and rather into something like cycles, just so you can actually see what's happening, I'll set up, what was it called, 5G approximation for slightly faster rendering, and then I can go into the shading editor where I can play with this lightning node. More specifically, I will increase the emission. I'll make the emission white, or maybe something yellowish, just so it looks a bit doper, and then I can change the emission strength. And now we're basically there. You can just kinda, yeah, this is your lightning. This is really your lightning, except it's not glowing. You cannot really make it glow directly in cycles. What you would really need to do if you want glowing is use Eevee. So you can go ahead and change this to Eevee and turn bloom on. And now you can see that we have lightning that actually blooms. There's a way to make it bloom inside cycle as well, but that would have to be a post-processing effect. So yeah, now we have a lot of control over this lightning. You can really play around with this. I urge you to do so. And another thing you would really want to do, if I go back into geometry nodes, is hook up all of the controls that are inside curves right now. So all of these controls, hook them up all the way to your group input, so you can control it from the modifiers tab. Currently, the direction of the lightning is determined by just whatever object has the modifier. Problem is now if I scale this object, it will also scale the lightning. So that might not be what you want. In that case, you need to have a switch in the object modifier. So that switch would be a boolean, and we would call it emitter. In which case you would just connect this up to a switch node as the boolean there, and whenever the value is true you would pass in, I guess, I have to give a solid example, don't I? So if in here I give it a boolean for this solidify, because we need to change the direction in which it is solidified, and then I pass in this boolean through a switch node, set this switch node to be based on a float, and then what we want is we basically want this subtract float not to be active, right? We want to turn it off. So in one of these paths you would take the node here, but in the other you would just go straight up like that. And this would be based on, well, this should be named like that, should be is emitter. So if this is the emitter, basically we want this to be flipped. So I guess if I turn emitter on, see how the direction of the lightning changes. So now it's thicker at the base. And you will also want to do this for the forking. For example, I would really call this is emitter. The only really other thing we need to change is the forking. You would need to change the parameter. So the way the parameter is interpreted from over here, literally the same thing. If we have the switch on, so connect the switch up. However, oh no, do you really? Oh, this needs to be float. Float. Important to have floats. Plug this here, factor here, and in one of these cases it will use this thing. In the other case it will just have to go through a math node that flips it, that flips the parameter. So subtract 1 to flip that, and this is the other case of our switch node, like that. So yeah, you can see that now we can change which direction the lightning is coming from, and now we can scale, well, rather we can just scale one of the objects that is receiving the lightning without the lightning changing too much, like the size of it more specifically. And yeah, I guess this is the tutorial. Thanks for watching. Please play around with this because it's pretty cool and you can really get some far out results with it if you just play around. Thanks for watching. There will be 2 more tutorials coming. One about getting lightning across a part, like that follows a path, so you can have even more control, and one where you have lightning arcing within a single object, which is slightly different from this, not too much, but it doesn't involve raycasting. And yeah, so thanks for watching. Subscribe for more, and I'll see you guys later. Bye.